Assalamualaikum warahmatullahi wabarakatuh. So we meet again in this series of lecture on numerical methods. So this particular lesson is going to cover on the topics of linear algebraic equations. So this is going to be consisted of several series of lecture. So I hope you can go through all of them. Um, so a little bit about the overview of this topic. So we're going to solve linear equations, okay, using several numerical methods such as Cramer rules, Gauss elimination, Gauss-Jordan, and Gauss-Seidel. So I shall demonstrate how each method will be used to solve linear equations. So I guess you're already familiar with linear equations. Okay, so all right. So this is the lesson outcome. So at the end of this topic, student will be able to solve problems involving linear algebraic equations. So these are examples of linear equations. I think all of us already familiar with what is meant by linear equations. Um, so the scope of our discussion. So we're going to find the solution for a few equations, at most three equations, three simultaneous equations, okay, using the methods that we have seen in the earlier slide. Of course, there is there is a quick way of solving these simultaneous equations if you use your calculator. Your calculator is able to solve at least three simultaneous equations. Just plug in the numbers, the coefficient of each unknowns. You will get the answer using your calculator very quickly. Okay, so I guess all of you have your own calculator, and each each calculator model has its own feature, so you can try out. So maybe after we use a particular numerical method to solve the problems, you can verify the answer using your calculator. Okay. Okay. So this is the first method, which fall under Gauss elimination. Okay. So as I told you earlier, this method is able to solve at most three simultaneous equations. So we cannot use this method to solve number of equations more than three. Okay, so maximum is three or less. Okay, so let's say we have these two simultaneous equation, okay, linear equations. All right, so there are two unknowns. So we can use this method to find the value of x1 and x2. Okay. Um, so that if you use graphical method, we simply plot each equations. Okay. So we will get two linear plots. Okay. The intersection of these two linear plots will give us the root or the solution for the unknowns. Okay. But there is limitation for graphical methods. Um, in the event where our linear equations do not give us a clear intersection points. Maybe they end up as a parallel lines, or they might overlapping with one another, or even though they intersect, but the precise point of the intersection um, is not very clear or very precise, in which we can pinpoint the exact location or exact points. So as you can see on the slide, there are three possible scenarios which basically tell us the limitation of graphical methods. Okay, so we can, so alternatively we can solve these simultaneous equations, okay, using numerical methods, in which we arrange the given equations in the form of matrix, and then we find the value of the unknowns, okay, by using the metric forms, okay, by finding the determinant of the metric forms. I will demonstrate to you the how this thing is going to happen. Okay, right. So I think it's good idea if we can jump straight to the first example. Okay, all right. So this is all right. This is example of two examples of um, metric forms. Okay, matrix A. So this is how it's being arranged. Matrix A 1 2 1. First row 1 2 1. Second row 3 4 minus 2, and third row minus 1 5 3. So as I said earlier, one method to solve simultaneous equation is using Cramer rule. So if we arrange our equations in the metric form, we have to find the determinant of the matrix. So let us find the determinant of matrix A. By the way, B is another example. Okay, so let us try doing metric A first. So this is how we find the determinant of matrix A. So we write down again the original matrix, okay, and then we write down another matrix, okay, next to it, which is taken from the first two columns of the original matrix, okay, and then we evaluate, or we find the sum of the multiplication of the numbers, okay, in the diagonal form. Okay, to see this clearly, um, what I mean is, okay, let's say this is metric A that we have seen just now. So we find the summation of the multiplication of numbers, okay, in the diagonal form. In this particular example, A1 times B2 times C3 plus B1 times C2 times A3, and so on. And then subtract or minus with the opposite diagonal, uh, okay, C1 times B2 times A3, okay, minus A1 times C2 times B3, and so on. So this is the techniques that um, that is used to find the determinant of A. So we get back to this A example of matrix A. So first we have to find the multiplication of the numbers along the diagonal of matrix A. So here we have, so 1 times 4 times 3 gives us 12, okay, plus 2 times minus 2 times minus 1 give us 4, plus 1 times 3 times 5, 15. Okay, and then we subtract with the diagonal on the opposite direction. Okay, here, so minus 1 times 4 times minus 1, we get minus 4, minus 1 times minus 2 times 5, we get minus 10, and so on. So the value of determinant A is 27. Okay, you can try out using the same approach with example B. So here we have matrix B. First row 1 2 1, second row 2 4 2, third row 1 5 1. And to find the determinant of B, so we write down again the original matrix of B, and then we rewrite the first two columns of matrix B, and put it side by side, and then we do the multiplication and summation along the diagonal lines. Okay, all right. So this is how we evaluate the determinant of matrix. Okay. Okay, let us jump to the first example. So we have three linear equations, simultaneous equations. Okay, as you can see on the slide. So first of all, we have to convert this line of equation into matrix form. Okay, so let me demonstrate to you using Excel. Okay, all right, this is the equations that we have seen in the slide. So we have to convert these equations, equation 1, 2, and 3, into a matrix form. So the first equation, 0.3x1 plus 0.52x2 plus x3 equals minus 0.01. Okay, this is how we write down the equations, or we convert the information from the equation into matrix form. So here, if you can see, I write down the first row in terms of the value of coefficient of each unknown, x1, x2, x3. So 0.3, okay, belongs to x1. So 0.52 belongs to x2, and 1 belongs to x3. Okay, so same things for the second equation, right? 0.5, 1, and 1.9 as their coefficient, okay, of for all the unknowns. Okay, this is the unknowns. We arrange them in a single column, and then the answer, okay, the results of this um, equation, we arrange them to another single column. Okay, all right. So this is how we write down the matrix. Okay, so to find the value of x1, x2, and x3, of course, as I said earlier, you can quickly get the answer using your calculator. So your calculator will basically tell you the answer within seconds. Um, but let's imagine that we are in the time of Isaac Newton, where we don't have this electronic device to help us find the solution. So we have to use Cramer rule to find the solution. Okay. So first of all, we have to find the determinant of our matrix. Okay, this is our first matrix. Okay, the original matrix that basically describe our each of our linear equations. Okay, so to find the determinant of this matrix, so we have to um, take the first two columns of the matrix and put it next to the original matrix and find the determinant. Okay, so we have to multiply the numbers along these diagonal lines. Okay, 0.3 times 1, 0, sorry, 0.3, okay, times 1 times 0.5 plus, okay, 0.52 times 1.9 times 0.1 plus 1 times 0.5 times 0.3. Okay, and then subtract with the multiplication of the numbers along the diagonal lines at this direction. Okay, so let me demonstrate. Okay, so this is the first step. in which we multiply all the numbers along the diagonal lines. Okay, and then we add them up with the next round of multiplication. All right, and then we subtract with the numbers along these diagonal lines. Okay, so we subtract with 1 times 1 times 0.1 minus 0.3 times 1.9 times 0.3 minus 0.52 times 0.5 times 0.5. Okay, so um, wait a minute, I think there is error here. Let me check. Okay, 1 times 0.1. Okay, so we have to put a bracket here. Hmm? Sorry. Uh, oh, here. Okay, I got it where I got wrong. It should be plus. It should be minus. Okay. All right. Oh, yeah. So this is the value of our determinant for this matrix, which I highlight in yellow. Okay. So the determinant of this matrix is minus 0.0022. Okay. And then we have to find the determinant of each x1, x2, and x3. Okay, so how we find the determinant of each x1, x2, and x3? Okay, so for x1, okay, so for x1, we write down again the matrix, the original matrix. Okay, this one. And then, okay, so since x1 is, if we arrange this whole equations, all of this equation in the metric form, so x1 belong to the first column. Okay, first column x1. So we replace the first column with the value of the answer here. Okay, minus 0.01, 0.67, minus 0.44. Okay, so I copy this. So we replace the first column with the value of the answer. Okay, and then we repeat the step that I have demonstrated to you to find the determinant of x1. Okay, so this is our new matrix for x1. So in which we have replaced the first column with the values from the answer here. Okay, And then next is we have to find the determinant of this particular matrix. Okay, this whole this whole matrix. Okay, so repeat the first procedure that we have just did um, just now to find the determinant of this matrix in yellow. So we take out the first two columns. Okay, right, first two column of this dx matrix and put it next to the original matrix, and then we do the multiplication and the summation that we have did just now. So like for example, the determinant of x1. So I denote the determinant of x1 in terms of the x1. Okay. Um, so we multiply all the numbers along these diagonal lines. Then add it up with the multiplication of the next of the numbers within the next diagonal lines. Of course, in real situation, we have to do this manually. But I in this particular, okay, for the sake of demonstrating to you, I use Excel so that you can see the works clearly and also to avoid error. Okay, then finally, okay, then we subtract with the multiplication of the numbers along these diagonal lines. Okay, so this is the determinant value of our x1. Let me tell you a trick, but of course this is a topic for another day for your lab, okay, lab computer lecture. So basically the quickest way of finding the determinant of matrix is using a function, Excel function. But and for the sake of verifying our answer, I can demonstrate to you how to do this quickly using Excel function. Of course, in exam you have to demonstrate the working by hands because you simply don't have this Excel function if you do the written exam. So actually there is an Excel function called determinant, okay, determinant, in which you can find the determinant of matrix in just a single click. Okay, so here I use function mDeterm to find the determinant of this whole of this matrix. So it gives me 0.0278, 0.03278. So it's so the one that we have done, okay, this one that we do it, we do the calculation manually, give us the same answer with using the Excel function. So we can have a certainty that what we have done is the correct one. So the same thing, okay, goes for the x2. So we have to take the original matrix here, and then since x2 lies in the second column of the matrix, so we replace whatever values in the second column with the value of the answer. Okay, here I've done it for you. So originally it was this one, but since I've taken out the second column and substitute it with the value in the answer, so we have here this value as the substitute in the second column, and then we repeat the same procedure just like we did for the x1. Okay, and you can also verify your answer. So if we do this manually, we get this 0.0649, and we can verify using mdeterm Excel function. Same thing here for x3. So I have substituted the original value in the third column, okay, with the one with the values of the answer, okay, 0. Minus 0.01, 0.67, and 0.44, okay, minus 0.044 in my third column. And then we repeat the same procedure, give us the determinant of x3. And finally, to find the value of x1, x2, and x3, okay, let's go back to the here x1. So we simply divide the determinant of the x1, okay, which is 0.03278, over the determinant of the original matrix that we have calculated earlier on, minus 0.0022. Okay, so we get the value of x1 as minus 14.9. Okay, so this is the final step. Okay, so we simply divide the determinant of x1 over, so determinant of x1 over the, we can say, overall determinant, okay, of the original matrix. Same thing for x2 and x3. Okay, so for x2, value of x2, so we divide the determinant of x2, 0.0649, okay, over this value of determinant that we have calculated as in our first step, during our first step. Okay, likewise for x3, divide the determinant of x3 over the determinant of value of determinant that we have calculated in our first step. Okay, just follow this formula. Okay, so so finally we get the value of x1, x2 of and x3, which are originally unknown to us. So using the Cramer rule, we have found the solution for each of these unknown, each value of unknown. Okay, so you can check whether we got the correct answer using your calculator. Okay, so I believe you can get the answer using calculator in a matter of seconds. All right, so that's all for the demonstration of Cramer rule on these particular examples, in which we deal with three simultaneous equations um, with three value of unknowns, x1, x2, and x3, using um, Cramer rule. So I will talk to you in the next series to discuss different numerical method to solve simultaneous equations of linear algebraic equations. Right, thank you.